Okay, so let us see how we handle this example. We are still on uniform rods. So uniform rod is mean, all we say is when the weight is occurring in the middle. That's all. So here I can see this one. A uniform rod PQ of mass 10 kilograms with a lower MQ resting on a rough. The moment we are rough, that means we have friction at Q. And the string is attached to its upper end P to keep it in equilibrium with tension T in the string as shown below. So that's what they are giving us. They are telling us that this one is at 45 degrees to the horizontal. Then this one is 15 degrees as you see. So find the tension in the string, normal reaction at Q, then the coefficient of friction. Okay, so we start by feeding in. You start by not giving us the length of this rod. So you say, let 2L be length of the cube. So it means that here I'm going to be adding my 2L there. Of course, because it's uniform, it's going to be having its weight acting in the middle. So the weight, we say we get the mass times the gravitational force, which is B. 10 times B, that's now the weight. If they give you weight, you don't need to multiply by B. If they don't give it to you, then you multiply with that B. Okay, so that's all we have. We also have, it's in equilibrium, and this is rough. So if this is rough, we expect, remember, if it's not equilibrium, we expect it to slide this side. So if the motion is going to occur this side, friction is going to oppose it to this side. So we have friction there. So because here there is contact, we are going to be having now this as the reaction at Q. Now that reaction at Q is going to be related to friction in that friction is going to be given by RQ, like that. Basically, those are the basics we have to handle. That's all. Now, we need to get the tension in the spring. Now, there are two methods. One, you resolve this here, and then here you resolve this T into this and this. Then you get a distance from here up to here, and then a distance from here up to here. Then you take moments at Q. Or you get a perpendicular distance from here up to here, which is the easiest method. So let me take you through the easiest. You try that in your free time. Okay. Now you see I have two forces here, this and this. So it's better I take moments here. So if I take moments at Q, you can take them clockwise or anti-clockwise, it's up to you, no problem. So let me take moments at Q. Why am I taking at Q? Because it has many forces, this and this, so it's better to take moments at Q. And now the other reason is I can ably determine the perpendicular distance from here up to here of this weight. So take moments at Q. Okay, let me take now clockwise. Now you ask yourself which forces are acting clockwise. Clockwise, we have this force, first of all, rotation is acting clockwise, but this one from this point now, for it is acting anti-clockwise. Now, if you take moments at Q, all the forces from Q, you see this and this, their moments are going to be zeros. Why? Because we don't, moments are given by the force times the perpendicular distance. So at this point here, these two forces don't have perpendicular distance. When I'm at this point Q, this perpendicular distance from here is 0. Then if I'm here, if this perpendicular distance from Q is 0, that's why we don't take moments. Their moments are 0. Okay, now I'm remaining with only this, but this one, I have this and I have that. So now it means that I'm going to be having T, I'm going to be having T times the perpendicular distance of T. That's the question. How are you going to get the perpendicular distance of T? Okay. The idea is, now I'm going to draw a perpendicular from this to my Q, to this force T, like this. If I consider this to be my perpendicular distance from Q, now it's perpendicular, so this one is going to be perpendicular. So if I need now of this length here, so I know that because this line here is horizontal, this is horizontal, means that this one is going to be 15 degrees. Now, if I have 15, I can ably get this. If this is, the whole of this now is 60. this is 60 and this is 90, it means the balance here is going to be 30 degrees. So if this is 30 degrees, then I can get this because I have the hypotenuse and I need the adjustment. So this one is going to be 2L cos 30 degrees. Now, the other way, you can now use this. If you have now this as your angle 60, it means that from here, you can get this. Now this one is going to be the opposite. But based on this angle, or it can be 2L sine 60 degrees. Now based on this angle here, because the whole of this is going to be 60. So it's up to you. It will be any use. So, but let us take this one off for theta. So the calculation is now from here up to here, we've got it as 2L cos 30 degrees. This is the only force which is going to act clockwise. It's going to be equal in 2 forces acting anti-clockwise using the principle of moment, which says the sum of anti-clockwise forces is equal to the sum of clockwise forces. So now our anti-clockwise we have 10d then times. Now we need the perpendicular distance from 2 to this. Now remember, if this is uniform, look at this. If this is uniform, it means that this is the middle. So if this is 2L, this is L, and this is going to be L. That's why whenever you let your length, you let it to be even. You can say 2L, you can say 4L. If it's 4L, this is 2L and this is 2L. That is the idea why you always let it be 2L. So that when you are splitting its field, if it's uniform, you can ably get these ones. Okay, so the perpendicular distance means now if I consider this triangle here, look at this triangle here. This triangle here, this one I have 15. Now this one is L, this triangle here. So it means that now I need this distance here. This is going to be now the L, okay? This, because this is the hypotenuse and I need this adjacent. So it's going to be L cos 15 degrees. That's why I'm going to put now L cos 15 degrees if I consider only this triangle here, this one here. And this, it is the case there. Then we are almost there. So it's that L is common, so I remove this L. So we see that my T is going to be 10 times 9.8 gives 9.8 times cos 15 the whole over 2 cos 30 degrees. And so my T here. You give 2 for the small places. So here the answer I'm getting is 54.6524 newtons. This is going to be my equation this week. So this is part A. Now part B, they want us to get the normal reaction. Now normal reaction we see is acting vertically. So it means that we have now to first resolve this here. So if I'm to resolve this, this is going to be now, if I'm to resolve it, okay, maybe I draw another diamond so that you can use that and you don't interfere with this. So I'm going to pause that video for some seconds. Okay, so now let's drawing this so that we don't confuse with it. So now you see, now our force are acceleration at Q. We need to resolve this now, this T. So resolving it means we can resolve it. This is going to be the vertical component, and then the horizontal component, you can put it here or here. So it's up to you. You can resolve it also in this direction here, in that direction there. So now the question is, how are we going to get it? So you know this is adjacent to this angle here. So this is going to be T cos 45. And then this force here is going to be opposite. So this one is going to be T sine 45 degrees. So we have finished resolving that. So what happens after? So we can start by resolving. We can start by resolving horizontally or vertically. Any. So resolving vertically, you see that we have this force and that force going up there. So we have T sine 45, then plus R cube. Because the system is in equilibrium, it means that now it's equaling to 10B. I call that my equation. And now I have T, I need R cube. We know what B is. So our R cube from there is going to be 10B minus T sine 45. So that our R cube is now going to be, okay, 10 into 9.8 minus our T. Our T from there is 55, 6, 5, 2, 4, sine 45. So my R cube from here is going to be, so it's going to be 59.3549 Newton. So that's the reaction at Q. So then, my part C, they want me to get coefficient of friction. But to get the coefficient of friction, I need to get friction first. Because I have R cube, but I need now to get this F so that I can bring that. So now this one, we are going to get it by resolving horizontally. Resolving horizontally, we have this minus this. So we have T cos 45. Is there another force horizontally? No. It's going to be equal to mu R. Mu R cube. So I have T. So that my mu is going to be T cos 45 the whole over R cube. So which is going to be, now R mu is going to be our T 54.6524 times this cos 45 the whole thing over R cube. Our R cube is 59.3549. So there my coefficient of friction is going to be so it's giving me 0.6512. So this is my coefficient of friction they wanted. So that's how we handle that. Now the other method of doing this, which is longer, you resolve this like we've done here. Then you take moments at Q. Take now moments at Q means that now you have this force, you have this force. And this one, because this and this, they are going to be, their moments are going to be 0. So need now the particular distance from here up to here, which you can get using this. You have this, so this is going to be 2L cos 15. Then now you need the particular distance for this from here. If this is vertical, perpendicular distance is horizontal. If this is horizontal, perpendicular distance is vertical. That's why you need this and this, which you have this, so this is going to be 2L sine 15. Then you simplify and you factorize out T, the same answer you're going to get like this. Anyway, that's it. I wish you well.